Hello and welcome. Today, we're going to crack open one of AI's smartest learning strategies, a technique that lets machines get better by, get this, obsessively focusing on their own mistakes. It's called boosting, and trust me, it's an absolute game changer. Okay, let's get into it. So, I want you to imagine an AI that's cramming for a huge exam. But instead of just, reading the whole textbook page by page, what if it could intelligently figure out exactly where it's weakest and then pour all of its energy right there? Well, that's the whole idea behind boosting. It's not just about studying, it's about having the perfect adaptive study plan. The secret to boosting starts with a pretty surprising idea. You don't actually begin with a genius model. Nope. You start with something called a weak learner. And you can think of this as a student who is, well, let's be honest, not exactly a star pupil. They're just barely better than randomly guessing. And as you can imagine, one weak learner on its own just isn't going to pass the test. So what exactly is a weak learner? In the machine learning world, it's often a super simple model, something called a decision stump. It's basically the simplest decision tree you can imagine. It asks just one single yes or no question, like, is the customer over 30? That's it. It's really simple, it's fast, but it's definitely not powerful enough all by itself. Okay, but here's where the magic really happens. The whole goal of boosting is to take a whole team, a whole committee of these simple, weak learners and combine them into one super accurate, strong learner. It's like the ultimate team-up movie, where a bunch of specialists together can totally outperform any single genius. So how do you actually assemble this dream team? Well, this brings us to the real aha moment of boosting. See, the key isn't just throwing more learners at the problem. It's all about how each new learner gets trained. Boosting creates that smarter study plan by forcing every new model to focus on the failures, the mistakes of the one that came right before it. And that philosophy, it's literally baked right into the algorithm's DNA. Boosting operates on this core principle that true understanding doesn't come from getting everything right the first time. It comes from methodically, obsessively correcting what you got wrong over and over and over again. Okay, so let's walk through this. First, one of our weak models takes a shot at the data. You can think of it as its first practice test. Then we look at every single question it got wrong. And here is the crucial part. The next model in the line is trained to pay special attention only to those errors. This cycle just keeps repeating, with each new student in the group becoming an expert on the exact problems the previous one couldn't solve. Now, there are a couple of different strategies for how these models focus on those mistakes. The two most famous are AdaBoost and gradient boosting. Just think of them as two different ways a student might review a failed practice test. And the difference in their approach is really fascinating. So you've got AdaBoost. Its whole deal is focusing on which questions were messed up. It essentially tells the next model, hey, these specific problems are extra important, so you better study them harder. But then you have gradient boosting, which asks, how wrong was the answer? It actually calculates the leftover error, the residual, and then trains the next model with the specific goal of fixing that exact amount of error. It's a subtle but really powerful distinction. So if gradient boosting is the study strategy, then XGBoost, that stands for extreme gradient boosting, is the star student who absolutely perfected it. I mean, this thing isn't just famous in the data science world. It's a straight-up legend. It has been dominating machine learning competitions for years. It is the undisputed valedictorian of the boosting class. So what's its secret sauce? What makes XGBoost so special? Well, it is just packed with brilliant features. It has these built-in rules called regularization to stop it from overstudying, just memorizing answers instead of actually learning the concepts. It's also incredibly fast because it's built to work on multiple things at once. It even knows how to handle missing information and can check its own work with something called cross-validation. It's just a brilliantly engineered machine for getting the right answer fast. Now, of course, boosting isn't the only way to build a team of models. Its main rival is a technique called bagging, which you might know from random forests. So if boosting is like that sequential study group where each member builds on the last one's work, bagging is more like giving the same practice test to 100 different students who all study independently at the exact same time. And really, the fundamental difference boils down to this. Boosting is sequential. One model has to finish its work before the next one can learn from its mistakes. Bagging, on the other hand, is parallel. All the models get trained at once, completely independent of each other, and then at the end, the results are just averaged together. This table really breaks it all down. You see, bagging is focused on reducing variance. basically making sure the model's predictions are stable and consistent. Boosting, as we've seen, is all about reducing bias, trying to be as accurate as humanly or machinely possible. Now, because of that intense focus on accuracy, boosting does have a higher risk of overfitting, of memorizing the data if you're not careful. But when you tune it just right, that's when it often achieves that top-tier, state-of-the-art performance. So, after all that, what's the final verdict on boosting? Well, like any brilliant student, it has some incredible strengths, but also a few areas where you've got to be a little careful. Let's take a look at its final report card. And the A grades here are seriously impressive. When it comes to structured tabular data, think of anything you'd put in a spreadsheet, boosting is pretty much the undisputed king, and that's why it's such a powerhouse out in the real world, used in finance to predict credit risk, in retail for forecasting demand, even in medicine to help diagnose diseases. It is fantastic at finding really complex patterns and can even tell you which pieces of information were the most important for its final decision. Okay, but it's not perfect, right? Here's where it needs a little improvement. Because boosting focuses so intently on its errors, it can sometimes get thrown off by noisy data or outliers. It might try way too hard to learn from what is basically just bad information. That same intensity also means it can overfit if you don't tune it properly, and its one-by-one, step-by-step nature makes it a bit slower to train than other methods. So, when you step back and look at it, boosting is so much more than just a clever algorithm. It's this powerful demonstration of focused, iterative learning. It's a method that literally turns a collection of simple models into a genius committee, all by obsessing over what went wrong. And it really leaves us with a fascinating question. If machines can truly perfect the art of learning from their mistakes, what incredibly complex problems will they be able to master next?